Take it away, Tom.
All right. Well, thank you very much, Sean and Sean. Boy, that was a lot of good stuff for those of us who love engineering and water heaters, and I'm definitely in that group. Um, and so now I'm going to try to take the gang through a little bit of work that's come up through a number of projects I've been involved in. And it's in working to retrofit electrification into existing houses. The issue keeps coming up. People keep being interested in panel upsizing for their main panel, or trying to stay on their existing main panel, especially in cases where they might have a constrained service feed, like maybe they're getting power from the utility through an underground line coming under a public road or something like that, which would be very expensive to replace. And so for those folks, they get very interested in fitting onto their existing panel while they electrify. And then in general, I'll show there's some great reasons for the rest of us to really look at how do we keep our amp draw down and stay on our existing panels. So that's really the issue here, that in that question, how might we electrify everything without expensive panel upsizing? And then the associated costly grid rebuilding. So just to give a little background and also disclose, I have this California bias, living here a long time. So a lot of things I'll say will be very California centric. So keep adjusting for other parts of the country or if you're there. My background as an environmental engineer in solar thermal and HVAC issues from Cal Poly, and got to do an internship at NREL, learn things there, and did a lot of building energy modeling. Got a license in mechanical engineering and was a utility planning engineer for City of Palo Alto gas utility and electric utility, doing resource conservation programs and demand side management, and also doing lots of their supply work, becoming their lead supply planner in their approach towards getting to the 100% carbon neutral electric portfolio. I retired before they finished that journey, but I was able to help them along it and part of it. I also am on the board of a nonprofit that does a lot of solar installations. So I like getting up on roofs with other volunteers and doing a little barn raising, installing solar. And that's where I learned about conduit bending and pulling circuits and things like that that have been very useful in electrification. I also still am in the utility industry. I do hydropower consulting for Department of Energy and Bureau of Reclamation, helping manage California hydropower and optimize it to work with the grid, getting it to start doing this double peaking that we need to be doing in the duck curve. I also do electrification consulting work right now through a couple of community choice energy groups down here in the peninsula, and I'm an environmental quality commissioner in Menlo Park, where we worked on a really interesting REACH code, and it's been helpful to a lot of cities. One fun thing I found to do is to try to figure out a little Venn diagram of, well, what drives me, or where do I apply different skills and experience that I've had. So that was fun, making a little picture of that. But back to this calibration about some things I'll be saying that apply definitely to California markets and situations, and then you'll have to extrapolate them to your own. But so most of my experience here is in California, and we have decoupled utility regulation, and that's common to 24 different states in the US. In decoupled utility regulation, the utilities are allowed a guaranteed rate of return on their assets, like their poles and wires or their gas pipes. Here in California, it's right now about 10.5% of the book value is allowed as profit to be taken by the utility. The rates are figured out afterwards. The rates are figured out as the cost of that return on investment plus all other expenses that need to be paid by the customers divided by the volumetric sales. And so that comes up with a rate. And because of this type of thing, rates will decline when sales grow. And so as we electrify everything, it'll put downward pressure on electric rates. The same thing happens in municipal utilities. Also, rates will increase when the assets are built. So if we're all upsizing our panels, and then PG&E in my territory or other decoupled utilities all over the country, if we increase our panel sizes, they see that as increased demand on their distribution system, and then they see the need to come in and maybe string new conductors. Or just 2 or 3 weeks ago, they were out in my neighborhood putting a new pole top transformer in place, a bigger one, replacing the one that had already been there, because of loads they're seeing growing in my neighborhood as electrification of vehicles is happening. So we've got these two competing things. Rates will decline when we get volumetric sales up, but rates will increase if we build assets. And then there's another effect too here in California. We're a pocket of cheap gas from the long-term fossil fuel industry that rivaled Texas for a lot of the middle part of last century. Texas and California were neck and neck as the largest oil-producing states in the world. And so we still have a large fossil fuel legacy and cheap natural gas, especially by worldwide standards. We also have this wonderful weather, this low humidity. The combined cheap gas and low humidity leave us with a very little heat pump experience here in California. So, heat pumps are new, and so we're looking at retrofitting them into homes. They haven't been built in. We also have great sunshine here, and rooftop solar economics are about 7 cents a kilowatt hour when you look at them over their life. And that's about a third of the cost of grid power. So solar is very attractive. It definitely helps your wallet to go solar. The duck curve, people talk about this curve of customer generation or customer demand minus the utility scale wind and solar intermittent renewables. Produces this duck curve that peaks in the morning around breakfast time and then dives around lunchtime as solar is satisfying so much of the load, and then climbs at dinner time. So we've got try to think of it in the 3 meals. We've got a ducktail at breakfast that's going to get expensive to meet. The duck back in the lunchtime, that's really low cost and clean power, easy to meet that. And duck head across dinner time, that's expensive again and not as clean. So far in California, we've had gentle weather, and hopefully the climate doesn't change. But the other thing going on here is kind of nice. The Public Utilities Commission is having rate reform. So they're taking into account the big duck, and the duck is impacting the value of the electric prices on the wholesale market. And so the PUC is starting to look at more duck responding rates that have these lower rates across the sunny hours of the day and then rising in the evening to encourage customers to use less in the dark and more in the daylight. The other good thing they're doing, they're getting off of the long-term prejudice against electricity, where they had up to 5 tiers of rising rates as you used more and more electricity. And now they're getting to flatter sets of tiers so that it's not penalizing the electrification. So some of my background comes from diverse exposure to a number of different things, having started out as a building energy modeler, doing solar thermal and efficiency modeling and Title 24 work, both on doing calculations for folks and then helping develop parts of Title 24 that looked at solar water heating and solving some of the problems they had analytically there back in the 80s. Then working on the power utility side, doing lots of analysis of power plants and utility portfolios of their supply programs and their demand side management, and doing this real integrated resource planning we used to do when it wasn't prescribed by the state legislature. We had to figure out our own balance of what is the right amount of efficiency and supply and of what types to figure out. And it's a great puzzle. So I really enjoyed doing all that work, and then retired from there. And so I've been doing solar installation work, and that led me to start looking at these main panel calculators. And so the Palo Alto Building Department had published one based on the NEC model, National Electric Code. And I was looking at just trying to read it, and it was so convoluted, and their logic seemed to go in loops, not circular, but there were eddy currents of loops of logic through it, where you'd have to calculate little pockets and whirlpools and come out and combine numbers. And I thought, oh boy, this can be clarified. So I went on to get interested in a kind of a hackathon thing the city did, and they didn't pick my idea, but I teamed up with Lisa Altieri, who started a company called Community Climate Solutions, and together helped her build a carbon calculator with a lot of different measures individuals can take to decarbonize their home. And in the process of calculating, the carbon savings and economics of all these different measures, I began to see how they interacted, how the amount of insulation you could put in would affect the amount of heat pump you would need, which would affect the amount of solar you would want, and these kinds of feedback loops. Her model, at the time, she wanted to get it ready on the market and didn't want to look at the interactions. So I've gone off on my own and developed the interactive analysis, and someday in the future I'll share that with this group. But the other thing that happened was I got involved with Carbon-Free Silicon Valley, looking at designing essentially survey tools for beneficial electrification, where we would be able to go into homes and perform a survey to figure out what it'll take to convert that home to electrification, and make this tool ready for electricians or home inspectors or a solar installer. So different folks who might get a chance to visit the home would be able to have a tool that they could use to help people figure out an electrification path. And so that's led to some other projects. I did get to team up with Menlo Spark and Sean and his team at Redwood Energy Partners in looking and helping on some of these guides to electrification, and that's exposed me to other good information sources about the types of products that are available to thread this needle on how do you do all this electrification and fit on your old main panel. And then most recently, I've been involved with Peninsula Clean Energy in a grant-funded project called the Peninsula Climate Comfort Project. And it's a beneficial electrification retrofit experiment on just a couple of homes. And it's spearheaded by Bruce Mast over at Ardena Energy. And then I was working with Build It Green and Home Energy Analytics. And the team of these four entities, if I count myself as one, we would go out to homes and look at them and start figuring out what the electrification path might be like for them, and what the panel analysis would be and what the issues would be. And some of our homes were very constrained with underground service to a 100-amp panel and things like that. So we had a lot of shoehorning to look at, and that led to a tool. So I have to back up because everyone else keeps talking about upsizing panels. And so I want to talk about how important might it be to thread this needle in the transition. And a recent study I've seen out of a Carnegie Group is saying that the existing fossil fuel infrastructure, including all the pipelines and vehicles, et cetera, but the furnaces and water heaters as well, if it's run for its remaining useful life, it blows through the 1.5 degrees Celsius climate safety goal. And now this is a big problem for human nature. The gist of the problem is if we run our fossil equipment for its useful life, it'll shorten ours. So we actually have to change one of our instincts. One of our instincts that has been to use equipment up and to get everything out of it. And I think we have to start looking at the climate as one of our pieces of equipment we can't afford to use up. We're going to have to incorporate it so that we will find a willingness to abandon some still running equipment. So to preserve this climate safety, we essentially have only one shot to decarbonize everything. We need to get the long run technology in place now. We can't go through too many intermediate cycles. We can't overshoot on the grid and cause us to rebuild it bigger where we don't need to. It makes sense to really try to get everything right. We need to have this low carbon electricity. We electrify everything, but we have to do it in a way that fits on the grid without needlessly upsizing. There will be places where we have to upsize the grid, but we need to do it without needlessly upsizing, because that will slow us down. If we upsize more than we need to, it'll raise electric rates, and that slows down the adoption of electrification, and that leads us into more climate problems. But looking at the gas side for a minute, if we're successful, the gas grid will be contracting to serve really just industry and a few winter power plants for a while. And I'm not sure beyond a few decades what'll happen there. But the remaining methane system will need a lot of work on leak elimination. But hopefully if we shrink the system, there will be less leaks to manage, and they will be able to get after them. And so, really what's at stake is how well, how fast, and how smoothly, without unintended consequences, we can do the transition. It's going to determine really kind of how much of the slide into climate change we're able to prevent. So I do look at it, the climate change it's not all or nothing, but it's really, we're working on the condition of our future. It's on this long carbon continuum. If we can get this right, we will be in a much better place than if we don't. Anyway, we all tend to know on this call that to preserve the climate safety, we're going to need to electrify everything. So here I've listed typical things in the home. And then I'm going to start talking about this term, an AMP diet, coined by Kelty Hiromi over at the city of Palo Alto when she was doing her own electrification project at home, and she found she needed to fit onto her service and had to look at all the different ways to do it. So the reasons to consider this AMP diet, it's analogous to considering things like embodied carbon in new construction, or even considering the refrigerant global warming potentials in the heat pumps. And the reason is there are, with both of those too, there are unintended consequences if you do things a way that you you didn't know about. So we really want to look ahead to where we want to be. And the unintended consequences of having large panel sizing is that they'll hamper our climate safety. They could get us into a loop of high electric costs that slow down the transition. And we don't want to do that. So the AMP diet thinking is going to provide some other homeowner benefits, like maybe lower construction costs. I'll show a couple of those, or lower equipment choices, the cost of equipment choices, and then maybe faster EV charging. If you think about EV charging as the last remaining load, the marginal load on the house, and if we can save a bunch of amps in other places, it leaves space for a larger setting on the EV charger. And they have these dip switches where you can set them from, say, 10 amps to 20 to 30 to 40 amps to charge your car at faster speeds. All right, so the classic mindset that we had when I started looking at this was, hey, I'm going green. I'll just put in a bigger main panel. And so that little blue arc on the left shows where that starts down at the bottom of the page, and it works our way up. But we start down there with that regular thinking of, okay, I'll just use the regular appliances I find. I'm trying to keep my costs down. And these may be large amp appliances in my conventional way of looking at it. And I'll put in a larger main panel. Well, that might have a bigger service line, that line connecting the pole to my house. Well, I may have to pay the utility for that. But the utilities noticing, well, they've got more load on the distribution side now on these feeders that run through the neighborhoods. And so they may need to upsize the wires and pole top transformers. Maybe not just for my house, but if I succeed at getting some of my neighbors interested in electrification, so we actually have a chance to preserve the climate. There's a lot of us doing it. And then if we're all upsizing, the utility sees the need to upsize those wires and transformers. That leads to bigger feeder wires, bigger buckets, and they rate base all that stuff. And they raise electric rates. And so then Also, it works its way up to the substations that we see, at the edge of town or different parts of a town. And they may have to upsize those substations with bigger stations and uh, more transformers in there and rate base all of that. So it's kind of building. So now this is the next picture, the bottom boxes we've just been through up to the substation level. But beyond that, the impacts keep growing. If these towns are doing enough electrification with big panels, requiring more distribution substation work, the utility will see they need more transmission to get more megawatts to the town at the peak times. And to do that, they build more transmission or upsize the wires on their transmission. They may build more peakers and more generation in general to try to meet these higher capacity loads instead of running the generation at a flatter output for the same energy. So all of that ends up leading to things where the price of electricity is getting too high and my neighbors can't afford to electrify and we can't complete the transition. So that's the problem that I worry about. So maybe we can switch over to another line of thought where, okay, I'll do some what I used to call smart amp stuff, but just because I like the short word. But I don't mean to confuse it with digitally interactive stuff. That's a subset of it, but just being thought through or astute. So here's the same process with an amp diet. The person tries to figure out what is the combination of appliances and control strategies and insulation levels and better coefficient of performance. What is the combination of those things I can use that can fit on my same main panel? And if I can find those, I produce a higher volume of electric flow over a smoother pattern that's better for the grid load factors. And that ends up keeping the same assets in play, but putting more volume through them. And that leads to lower rates, lower than they would have been. And then this keeps trickling up by not having to rebuild the distribution system. I also don't have those rate increases. I also make a nice flatter load shape or more load in the sunny part of the day. Also, that can lead to more renewable generators. So a better and essentially less battery storage to move cheap solar to the nighttime duct head when it's going to be needed. So those kinds of things also keep rates down compared to not doing them. So then rates are okay for everyone else to electrify and we've got our happy climate. So that's some of the reason for the amp diet. And now we'll back off to, just in case people don't know, we'll talk about what's an amp. And so really what we want is safety in our homes. We don't want overloaded wires. And we want safety between our house and the pole too. So that service wire, we don't want it overloaded. Overloaded wires heat up and they cook their insulation. That's what's bad for the safety. And so that's why we have all these requirements for wire sizing and amp and main panel amp ratings and those kind of things. We're trying to size wires stout enough with a big enough cross section and conductivity so they have low resistance to the electric flow and they don't overheat. So they don't cook their insulation. And once we picked a wire size anywhere, then we limit the amps that are drawn to flow through it by the device at the end. We limit those amps so that they don't overcook the wire and make it unsafe. So the downstream equipment is what's demanding the amps, and we pick the equipment to be below the safe wire size. So that's what's putting constraints on our equipment sizing and the amount of electrification we can do. We have breakers in our systems in our main panels at the circuit level and also at the service line level to our main panel. These breakers protect the wires from this overcurrent draw. All right, got only one page of kind of like physics. That's what the little tilde is there. So the wires have resistance to to current flow. The resistance causes the wire to heat up. If the wire overheats, we have the safety problem. The current flow is measured in amperes, which is a coulomb per second, or it's a watt per volt. And you don't need to memorize that part much, but wire heating really happens as a function of the amps squared times the resistance in the wire. So there's that formula. Or it can also be displayed as the power equals the current times the voltage. And the current can be thought of as the power divided by the voltage. These formulas show up occasionally when we're doing the work, just to try to show how units convert from one to the other. But the National Electric Code is setting the safe amp limits on the wires, the breakers, and the panels, those kinds of things. They're setting those limits and telling us whether we're, if our desires to electrify are going to go beyond the limits of our existing panels or our planned panels. So that's where that's coming from. A little bit of the nomenclature is that we've got up in the upper right, say, imagine a pole, and you can see a little roof line here and a wall. So this wire from the pole is called a service drop or a service line, and it's carrying the current to the house. It goes into this metal thing you see up through your roof called a weatherhead, where the wires come under it and go down to the meter socket. The meter plugs into the meter socket, and below the meter, in this case, is the main panel. At the top of the main panel, and most of them, it has a main shutoff, and then below it are branch circuits. So that's a little bit of the nomenclature. Here's now a closer view of the main panel. That little arrow is just saying this big box here is the main panel. And it's got the service lines coming from the pole. My arrowheads are going the wrong way. Most of the current's flowing in here. We've got two different energized lines, the labeled down here, line 1 and line 2. They're both at 120 volts relative to a neutral line that's called a center tapped neutral that goes to the center of the transformer and gets a 0 voltage all the time. And then the sine wave oscillation between the cycles, 60 cycles per second, is oscillating line 1 and line 2, 120 volts on each side of that neutral. And so they're able to do that, and by just collecting, putting our circuit breakers across these different parts of the panel, we get either 240 volts, the full 120 plus 120, if we put a circuit breaker across line 1 and line 2 and feed it out, we can get 240 volts. Or if we put it just across one of the lines and the neutral, we can get 120 volts. So your panel's got a number of these 120 volt circuits going off to lights and plug loads and things like that, and some of these 240 volt breakers going off to the bigger loads. And so I can show here that a 12 gauge wire for some distance is capable of carrying 20 amps at 240 volts, which is 4.8 kilowatts. The same type of 12 gauge wire on the 120 volt circuit is able to carry also 20 amps, same as the other one, and that's only 2.4 kilowatts available on those circuits. So that's the reason for having some of these high voltage circuits in the house, is they can deliver more power to the load. So that's going on now. Now we'll start talking a little bit about the main panel calculations and trying to how do we go about doing those? Yep, there we are, back to amp map. So this is the first of the amp maps. I'll show it a couple of different ways. The main panel amperage needs to be equal or below the service line amperage coming from that pole. So it needs to fit there. They really can't size those to be larger than the wire from the pole can handle. Otherwise, you could draw more than the safe amount across that wire. It would overheat the insulation, and the squirrels would burn their feet. Or worse problems could happen. A fire could happen out there on the pole. So main panels are sized below service line carrying capacity. Then coming down here from the solar industry, I noticed all the time solar can be sized only up to about 20% of the main panel amps if it's put in through a circuit breaker. It could be sized larger than that if it's line tapped, not onto a circuit breaker, but onto the line, say, between the meter socket and the panel. I'm going to ignore solar from here out, but lots of these panel calculations, I'll get to it in a little bit, lots of them have different amounts of how many of the first kilowatts they're counted at 100% coincident, meaning occurring at the time of peak for the house. Some of them are down at, they only count 3 kilowatts as counting at the peak, and everything else would be 40% load factor. And that leaves us lots of space then to put more loads that only count 40% as high. The reason they only count 40% as high is not everything on your house is on at the same time or assumed to come on at the same time. If it all did, the main panel breaker will just trip and protect the panel and the wires to the pole. But that's a very rare event, especially, I just noticed that just doesn't happen that much. We tend to size things, pretty generously for lots of space. But there are different assumptions I'm finding used in different versions of the NEC code for how many kilowatts of load are counted as being 100% coincident and on with each other, and then how much is left over to be counted as only 40% coincident. There are two kind of special case loads. One of them is EV charging. So EV service equipment is counted with you see 125% safety factor multiplied by the normal 40% coincidence factor, or they call them demand factors, but they're really coincidence factors. So when we multiply 1.25 safety factor by the 40%, we get a 50% equivalent. And then the other load that's assumed to be on, totally coincident with a building peak, makes sense, is the larger of either the heating or the cooling. So here again in my Bay Area, California bias, it'll be the heating, which will be larger than the cooling. And so it's counted in your load calculations as being 100% coincident. And then we'll also look at it at the design condition. So on that very cold day or very cold morning that it's on, fully on and loaded. Okay, so another way to look at the counted amps would be that these amps are the watts on the nameplates of our devices for plug loads of just watts divided by 120 volts, or for the big draws like the EV charger and heat pumps. That a lot of heat pumps are 240 volts, and the range for cooking is 240 volts. Those all have the watts divided by 240 volts will give us the amps, and we multiply by those coincidence factors, either 100% or 40%, or the strange one, 50% for EV charging. Okay, so let's see, Sean, are you still there?
Yes, I am still here.
Yeah, so I just thought I'd pause for a moment. I've seen a few chat questions come up, but I don't know if I should break for those or continue on.
I think the questions haven't been so much as just first a comment that you are brilliant, Tom Kabat, and then HEA, I think that Steve said seconded. I just say thirded. You're doing, you're brilliant.
Okay.
You should note that you have about 23 minutes left.
Okay.
So just time back for you. There you go.
I will power on. Thanks. All right. So anyway, the way they work these calculations, they start out with the number of square feet in the house, and they just assume there will be about 3 watts of load per square foot of the conditioned space of the house. So you don't have to include the garage. And that's to cover the lighting and plug loads and roads and rooms. And then in the kitchen, they assume you'll have at least 2 small appliance circuits on your countertops uh, to run devices, the blenders, the toasters, things like that. There's also assumed a laundry circuit. And the thing to recognize in the laundry circuit is it holds the washing machine or combined washer dryer. That washer or dryer gets counted as that one laundry circuit, which is deemed to be at about 1.5 kilowatts. So there's a good, that'll come up as an interesting opportunity in a few minutes. Other connected devices are counted at their nameplate watt ratings times this 40% coincidence factor. Then I mentioned we count the larger of either heating or cooling at 100% coincidence factor. EV charging is 40% coincidence times a 1.25 safety factor counts as 50% of the rated watts.
Now,
Okay.
now's a good time to ask you a question from Dan Johnson, who said, Tom, do these formulas come from the California Electric Code service sizing? Because doesn't this count electric vehicles at 100% continuous load?
Right. I keep seeing the counting as 1.25 times the 40. And so I would like to check in with Dan, because I do think of this as a conversation where other people see other things. And I've seen different cities implementing these things very differently. So one of the things, I'm going to put a plug out for us all trying to influence the NEC by September of 2020 on their next code cycle. And then also trying to work with cities. I think there are some things we can do to make electrification easier for folks. So let's talk about it. But so far, I'm just using 1.25 times 40% to get 50%. So, and here it is showing up again, center box right here, EVSE. So this is another view of the amp map, just concept I'm trying to fiddle with, where heating is viewed as 100% coincident, EVSE 50%, and all else 40%. Then I'm breaking that out down below, the green boxes, just to solve that mystery real quick. Each of the green boxes have choices in them where you can also save energy as well as amps. And so there might be economic and carbon reasons for looking at working in the green boxes. The deeper the green, the more important it was. But here's an interesting example, the cooking range. So cooking range means to combine a cooktop and an oven into one device. It doesn't necessarily save energy. It does save a lot of amps. And so that's one of the things. The other, other places we can look for our decisions on where to do our amp diet is picking high coefficient of performance heat pumps will save amps. Getting good R values, insulation in our design for our building shell. Going ductless saves a lot of amps because then you don't have all the duct loss from conduction across the duct, the thinner insulation on ducts, and the leakage and the fan power. So ductless systems may be a big amp saver. Locating ducts in the attic looks pretty bad, but putting it down in the crawl space looks better, just for energy reasons and conditioned space temperatures, etc. A heat recovery ventilator can be an energy and a small amp saver, and then blowing your heat recovery ventilator towards your heat pump to have it be providing some warmer air to make your heat pump think it's in a better climate. That can also save a little. Switching from your dryer from resistance to heat pump dryer saves some, and it also saves energy. Getting one of these combined washer dryer single machines saves a bunch more amps and a circuit and circuit space and energy. So, and money and floor space. I mean, it's kind of an amazing device. Okay, I'm going to drill down into heating for a minute. So heating counts 100%. So then the design conditions around here, around 30 Fahrenheit, is what we're designing for. And so we want our heating, it's going to determine our heating loads. So we really want to have good R values, good windows, things like that. On the air side, we might want to look at heat recovery ventilation and real air sealing. On the duct side, I've said going ductless is great, crawl space is next best, attic is worst. On the COP choice, going and really pursuing good COP equipment might be a big money saver for you. So take a look at it just in saving energy and amps, and then look at compressor location. That's for future studies. I'm working with a Stanford team on the benefits of crawl space as a location for heat pump compressors. So here's a little chart of just looking at heat pump coefficient and the building UA, so the inverse of R values and all the wall areas, et cetera, and windows and all that. So the whole building UA, including infiltration. And then what I've done is I've done what is that? I guess a 10% improvement in heat pump coefficient in each line, working my way down, so I can double from a 2.5 COP piece of equipment to a 5 COP. So that's a doubling of COP, and you can read across here on the amps. It cuts the amps in half from 19 down to 9. And then across the bottom, I'm also looking at improving the building UA by increments of 10% each block. So 7 blocks gets me down to heat loss is half as big down here. So I've really done the same multiple. It's a 100% difference in coefficient of performance there, and a 100, a doubling. Well, they call it a doubling there and a doubling there on the building UA. And so what I'm showing is the two are interactive, and they're also about the same magnitude. Each one can cut your amps in half. But also there's an interesting thing. The design heat loss, I show a small arrow down here at the great building shell end, and a big arrow, lots of heat loss at the looser building shell end or bigger building. So that's got a certain amount of vulnerability to it when you've got a large heat loss. And whereas if you're down here at the low heat loss side, you've got a lot of resiliency. The other thing is, down at the low heat loss side, your house can act as a better thermal battery. At the loose house size, it's hard to use your house as a thermal battery because it's leaking it too fast. So that's just a couple of things to think of for the interaction of building UA and coefficient of performance. They're not exactly equal because building UA can build resilience that coefficient of performance cannot. All right, here's I besmirched ducted systems. So here I'll show the little bit of evidence for it. Here's the house with the same insulation level, so I'm not going to change that. I'm going to look at the impacts of central distribution versus ductless. And I'm going to look at a few different COPs. So these are COP. Let's see, what have I done with COPs? Oh yeah. So here's the coefficient of performance is this sloped line, and so there's 3 axes really shown on this right-hand axis. Let's start with coefficient of performance. Here's a coefficient of performance of 4 up at this end, and down at this end it's 2.5. And so I'm just picking a few points on the coefficient of performance, either a poor piece of equipment down here, which has high amps, versus a high COP piece of equipment there and has lower amps needed. And then these 2 lines with X's in them, those are both read to the left scale. Those are kilowatt hours per year. And you can see with a bad bad COP, I use more kilowatt hours a year, and a good COP, I use less. And then tons, the ton sizing on the 2 things. Here, if with my ductless system, I only need this 1.9 tons, and I need about 2.2 tons if I have a central ducted system. The reason is my ducts lose heat. And so I need the tons to replace the lost heat and the lost infiltration air from the ducts. And then the same thing with these, this is ductless energy, and that's central ducted energy. So there's a different amount of energy needed per year for a ducted system, and here for amps. There's more amps needed for a ducted system and less for a ductless system. So that's my little pitch to explore ductless when you can, just to save all of the problems with the ducts. And it kind of does assume, it's best here if I disclose, I think I'm assuming you get the refrigerant lines into the building shell, so they're not in the attic or losing some heat. Okay, a great source of heat pump data to try to see how do heat pump coefficient of performance change with different conditions is this NEEP, Northeast Energy Efficiency Partnerships. Go to this website, you can find thousands of heat pumps and how they perform at different temperatures. Okay, this is just a little plot showing how heat recovery ventilator can save carbon and about 1 panel amp for every 60 CFS that you're recovering from it. And it's probably a little complex for the amount of time we have left, but the nice thing is it's energy savings across the 24 hours of the day. They're peaking at that morning tail peak. They're down in the middle of the slack day, and then they rise again in the dark. And so it's kind of a neat grid-friendly device is heat recovery ventilators. They save more when the grid needs you to save more, but they only save about 1 panel amp per 60 CFS. On the heat pump water heaters, we really found in our projects a big benefit to having the 15 amp type of heat pump water heater instead of the 30 amp type that had 2 resistors. They both have, say, a 500 watt heat pump, and they both can deliver about the same first hour rating for gallons per hour. But we found that you get better results getting the biggest storage you can into the space and using the least amount of resistor you can. The storage helps meet your load, as Sean Owen was going over. So that's a great way to do it, is more storage, less resistor. Here's the example of the picking instead of a separate cooktop and oven, both electric, having 40 amps and 40 amps, 80 amps. If you buy the thing they call a range, which is one appliance with a cooktop built onto the oven, it only needs 40 amps. There's internal power management going on in this device. It's free. It's cheaper than free. One range costs less than an oven and a cooktop cost. It also saves 2 breaker spaces. So it's saving 40 amps, well, times 0.4, that's only 16 panel amps, but it's saving those amps plus 2 breaker spaces. The other great combined device is this combined washer dryer. At my house currently, and it's under negotiation, but we currently have a washer and a dryer. And so the washer is using about 6 panel amps and the dryer can use 30, so a total of 36. But if I can convince my wife that we can switch to the combined washer dryer, it'll save 2 more breaker spaces and it'll save those 30 amps by getting us down to just using roughly the six panel amps, about 12 amps on the 120 volt. So then that can start the ability to start a savings cascade. So here's the cascade of, you've got your garage, maybe you've got a dryer outlet and a washer outlet. You get one of these combined washer dryers, that frees up the dryer outlet. You put a plug sharing device in there, like the NeoCharge device that shares between, say, a water heater and an EV charger. And what it'll do is when the water heater resistor is running, it'll pause the EV charger. Well, the resistor only runs an hour a day, maybe. So there's another 23 hours a day the EV charger can be running. Together, they're both on that one circuit that you freed up by getting this one device. So now you've freed up 30 amps down there. But anyway, adjusting it all for panel amps, you've saved a total of 24 panel amps and 4 breaker spaces in the panel. Here's another combined cascade too. You could start earlier. This is now a 220 volt circuit coming from the panel to a plug share device like the NeoCharge, where the range is now dominant. When it's on, it pauses the whole other flow to the garage circuit, but my range is not on that many hours a day. We're cooking what, 1 hour, 2 hours a day? And so the other 22 hours a day, there's power going here to the dryer outlet. It can then feed the rare event of the resistor in the water heater. And most of the time, probably more than 20 hours a day, it's there for the EV. And so in this case, I've saved 40 panel amps and 4 breaker spaces. So these are the types of combinations we can do to keep costs down. Because we kind of have these fiduciary responsibilities to the homeowner to make progress attractive so they'll participate in saving the climate. To the utility, so they don't raise the rates. To society, we've got to quickly reduce emissions and avoid long-run damage. So, really we need to be looking at doing all reductions that are costing less than 200 or 300 a ton. So what if we go big? Everything has to grow. And it leads to a spiral of utility rates growing, more people installing what I call naked solar, which is how I installed mine. I had my clothes on, but the solar's up there. I did the solar days before the electrification, but if people just install solar without electrification, they become bad gridizens. And we want them to be good gridizens who install electrification and solar. Okay, if we go smart instead, so the choices are go big or go smart, we start fitting everything onto the existing panel ampacity and designing new homes to be low ampacity. We can save, say, $3,000 in retrofit by not having to upsize the panel. Peak loads will be naturally lower and shaped lower, and often energy will be saved as well. And then we can deploy part of the savings into controls. And some of the devices like these ranges and combo washers are already cheaper, and they have built-in internal controls. So NEC's trying to produce what I call micro safety. They're trying to prevent the 1 in a million chance that a home will have an electrical caused fire by having a malfunction in the protection systems of the panel or the line, that kind of thing. Whereas a lot of us on the call, we're looking at macro safety. We're trying to save ourselves from the climate, prevent whole communities from burning. So we've got different areas, but we need to get them looking at ours too. Let's see. We'll just keep moving along. We've gone over some of that. Examples of load calculations. Maybe I'll get back to that. Okay, so here's some choices. So I've said instead of, this column is use this instead of separate oven and cooktop. Just see, we've gone through a bunch of these. Combined washers, dryers, I like that idea. Improved insulation can save about 2 amps probably instead of a larger heat pump. Ductless heat pumps, in some examples, try your own, but I'm just seeing, on the order of, say, 3 amps. Better heat pump, better COP heat pumps, maybe another 2 amps. Try to avoid the ones that would have resistance power for either backup or defrost.
And real quickly, we saw that the heat pump water heater model that General Electric is coming out with, the one that's
the 120,
900 watts, I think total is what that goes to.
Yes, yeah. So that's good to see them back in the market and with a great product. So look forward to that. Better windows can maybe save 6 amps. So I'm just giving a list of these types of things. This NeoCharge or Dryer Buddy type device, 2 different companies, they can save maybe 30 amps. And then this other device we started looking at before is a electrician installed thing called a DCC9, and it's an EV pausing circuit. So it pauses the EV when the whole panel gets to within 80% of its rated load. So that's kind of an interesting alternative. Here's drain line heat recovery idea. It can probably save a little amps or let you get by on that little GE water heater. Drain line heat recovery in some big households could be the difference between fitting onto that 9 amp water heater and not fitting. Other things are interesting, and like better refrigerator with a lower nameplate might save 2 amps. Better dishwasher, smaller garbage disposal. They sell 3 sizes. So, and those things count. So there's ways to save there. I look forward to John Sarter's two-way EV charger. I'm not sure how it fits yet onto which side it's on this, so it depends on the controls. Solar Edge has an interesting product that combines a solar inverter with a car charger that maybe can give you faster charging in daylight hours and save some amps. Oh, so people are looking at resilience, and they're thinking of putting wall batteries on as different ways. So a wall battery put in just as backup or arbitrage counts as 20 amps loaded onto the panel because it is a load, and it may occur during the time of everything else being on. But if you've got a battery configured as a panel supplement with controls that have it discharging when the panel is at high load, it can count as relief. So that's going to be a big difference. This is a 40 amp swing between how your battery is configured. And this is just my theory right now because I don't know too much about how the commercial products are placing themselves. I'll have to get back to this one later, but I'm really excited about the possibility of utility meter located batteries that would be shared between the utility and the customer, and they would try to capture lots of the value stack that RMI has identified by getting the two parties involved and having them operate to optimize. I am seeing, as I go just look on the web, see lots of different authorities having jurisdiction, these AHJs, the differences in what they're using for their main panel sizing calculations, differences in how many of the first kilowatts count as 100% coincident, and what their coincidence factor is for heating, for EVs, and for all other load. The most egregious I saw published by Gilroy, I don't know if they've just had, made a mistake in what they're saying, but they just count everything as though it's all on, and there's no diversity recognized at all. But other agencies have different amounts of diversity recognized, so there's room for us advocates to go work on what is the best solution for macro safety, or total societal safety, combining macro and micro. Here's one little interesting plot of what happens as you try a path of what are the path of incurring costs or savings and accommodating amps. And so this little spot way over here is $3,075 amps. So that's the cost to upsize a 125 amp panel to a 200 amp panel. Doesn't save any energy, it just upsizes the panel. And then here's an alternative approach to add ampacity and get electrification in. It would be first, and here's the items. The first one, using a range instead of separate oven and cooktop. Saves 16 amps and $1,000. Then the combination washer dryer saves another 16 amps. Oop, there it is, 16 more amps, and a bunch more money. And so it saves, this is capital cost here. Using a 15 amp water heater instead of a 30, so just looking at Rheem's models and just picking the 15 amp Rheem versus the 30 amp, doesn't save any more capital cost, but it does save another 6 or 7 countable amps. And so there it is.
Tom, I want you to be able to wrap up because we got Lily waiting on the wings here.
All right. So anyway, but just showing that you can plot a path of how you get through this adventure. And the last thing I'll just show you, there is a spreadsheet associated with all this stuff, and it looks kind of like panel sizing spreadsheets, and it just takes people through what are the loads, the devices, what their common loads are, what their volts and amps are, and you can input different things, whether they're using single or double poles, what their minimum breaker sizes are, etc. And then we just count up all the right coincidence factors for them and look at the case of different cases and just try to see how many remaining panel amps do they have left as we try different electrification circuits. So that's the basics of really diving into the the available devices that you can find in Redwood Energy Partners Guides to Electrification, and then use that to try to shoehorn onto panels so we preserve the climate. Thanks, everyone.